So, how many dimensions do we live in? Fingers. Hold up fingers. 3. Interesting. Okay. Not acknowledging that. So, motion is a question that I have for you. Let me cancel that. The question I have for you is about this marker. I'll take a picture of it here. And the question I have for you is the marker moving? Don't answer me. Answer somebody else sitting at your table. Yes, it depends on what it's relative to. So it's on the Earth, and I heard several groups say, well, yeah, the entire Earth is revolving. And so, yes, it is. The Earth is rotating on its axis. Now, it revolves around the sun, rotates on its axis at, what is it, like 1,000 miles per hour at the equator. And we're a little further north, so we're going a little slower because we're off the equator. So, yeah, it's moving just like we are. But, you know, the sun is not our most common frame of reference. The most common frame of reference we use is the Earth itself. Because little creatures with little pinheads such as ours really can't perceive motion around the sun. I did have a friend years ago whose hobby was laying down in fields facing east in the evening, looking at the stars and going, whoa, I can barely hang on! Which she found really entertaining. You know, if you stay there long enough, you do see the stars rotate. But we tend to think of motion in a frame of reference to the Earth. So, relative to the Earth, is that marker moving? No. Just sitting there minding its own business, hurtling through space at 1,000 miles an hour. That's important because when we talk about motion, we do have to specify frame of reference. Who here has ever been on a bus and had to walk down the aisle on a moving school bus? Are you moving? Yes. In relation to the Earth? Yes. In relation to the bus? Yes. You're moving in relation to 2 frames of reference. So the motion that we describe can happen in up to 3 dimensions. We actually are said to live in 4 dimensions, the 4th being time, which we perceive, but we don't perceive it spatially. The motion that we're usually describing does happen in 3. And we describe them on a Cartesian coordinate system. I would invite you all to stand up, unless you're dizzy, and then just stay seated. Because we're going to do the Cartesian Axes dance. Some of you who've tolerated me for a year prior to this already know this one. Okay, so we typically describe the X, the Y, and the Z axis as the axes on which we perceive and describe motion. For this chapter, we're only dealing with 1 axis at a time. In chapter 3, we take on 2 axes at a time. We don't do 3 axes in here. That's way beyond our scope, and it's horrible, and you would cry tears of blood and your head would explode. It would be very, very, very bad. But, you know, if you're going on to an engineering program, have fun. Those are usually actually modeled on computers because doing the calculations for 3 axes of motion at a time by hand would make your head blow up. So we're only going to do 1 axis at a time here, and once you're really good at that, we're going to throw a 2nd axis into the mix. With 1-dimensional motion, and we're going to start off talking about the x-axis. With 1-dimensional motion, you can think about a train on a railroad track. You can think about anything that's sort of affixed to a straight line path of motion. And it can't go left or right, and it can't go up and down. It just goes back and forth. That's what we're thinking about, is just back and forth motion right now. Displacement is where you end up minus where you started. And this is a number line thing. So if we call this 0 meters, 2, 3, 4, 5, and this 5 meters, if your little object or vehicle or whatever it is, we'll make it a box, goes to 5, and goes back and ends up here on 2. The overall displacement is the final x position minus the initial x position. We talk about this as delta x. That's how we refer to displacement, because it's change in x position. So in that case, we would have 2 meters minus 0 meters. We would have a delta x of 2 meters. But we went to 5! Doesn't matter. 2 steps forward, 1 step back, you only got 1 step. Displacement is really important as differentiated from distance. Distance is a little different because distance literally counts the steps you took. It counts the actual road that your tires touched. So if you start here at the high school and you drove every back road known to humanity, stopping at every friend's house you could possibly imagine, doing every side errand and investigating everything, and ended up in Calcutta, your displacement is just that. It's the difference in your initial and final position. It's not the same as the distance you traveled. So your car's odometer, for instance, records distance. Race cars go nowhere really, really fast. Nothing like spending an afternoon getting nowhere at high speed. That's what they're doing. That's why I think it's the stupidest sport possible. I don't even, well, anyway, that's a whole nother conversation. You wake up every morning at home. That distance doesn't count for a whole lot here. The displacement is the more critical piece. So velocity is what we use to describe the rate of how fast you're getting someplace. It's the rate of motion. And we will start off using average velocity, which is displacement divided by time interval. It seems like maybe you just did that. We can show that as VA equals delta x over delta t, or VA equals final x position minus initial x position divided by final time versus initial time. One of those can be 0, but they don't have to be. You know, we can use, those are kind of arbitrary. And our 0 position is kind of arbitrary. And then we'll talk a little bit about negative motion. So I'm going to right now stop this video. I'm going to have you take your recall quiz. Look over your notes and discuss them real quick. See if there are any questions that you have.